Hello, everyone, and welcome to Lecture 20 of GPU computing. Today, we're going to talk about an advanced programming technique, and that's intra-warp synchronization. So as a recap of what we've done so far in the course, we started off the course in the first 3 weeks, where we looked at some of the fundamentals of GPU computing. We looked at the architecture of GPUs, we looked at the basics of the CUDA programming model, and we also looked at the various key optimizations that people apply in different for different applications. And then we took what we learned and we spent around 7 weeks going through various parallel patterns to see how we parallelize different applications with different patterns. And we used a lot of the techniques and the optimizations that we learned in the first part of the course. So I hope by now that you've gotten a good idea of how we go about taking a particular application and then starting from scratch, doing a basic parallel implementation, and then incrementally optimizing it until you get an optimized version. In fact, this is what you guys have been doing in the project, and you know we're in the next part of the course. We won't be looking at new patterns, but we're looking at some advanced features, and maybe some of these will help you with some of the advanced optimizations you'll do in the project. So we're done talking about parallel patterns, and today we're going to begin talking about some advanced features that GPU programmers might use to optimize their applications. And today, in particular, we're going to talk about intra-warp synchronization. And here, intra-warp means within a warp. So we're talking about synchronization within threads of the same warp. So if you remember, when we spoke about warps, we said that warps are the unit of scheduling in an SM, and that the size of the warp is device specific, but it has always been 32 threads. And the unique things about threads within a warp is that they execute following the SIMD model, which means that we fetch one instruction and we execute it for all threads in that warp, and these threads execute on the SM, on the cores of the SM at around the same time. Now, because warps execute following the SIMD model, because the threads in the warp are executing at the same time on the SM, we can take advantage of that by synchronizing between them more efficiently than, for example, we synchronize across threads in an entire block using sync threads. And this brings us to the topic of intra-warp synchronization. So we can take advantage of the special relationship between threads in the same warp to synchronize between them quickly. And CUDA actually has several built-in functions to synchronize between warps. And there's two kind of major categories of functions. We have functions that share data across threads. We call these shuffle instructions or shuffle intrinsics. So basically what we're doing here is we're shuffling data across threads. And what we mean by sharing data across threads, obviously threads can already share data through shared memory, but here what we mean is actually sharing registers or register values across threads. So a thread can take a value in one of its registers and send it to another thread directly without going through shared memory, as long as that other thread is in the same warp. We can also do things like voting across threads. So maybe different threads have some threads have different threads maybe check some conditions. Some of them are true, evaluate true for that condition. Others evaluate to false. So if you want to figure out how many threads evaluated to true and how many evaluated to false, or even which threads were true and which threads were false, or something else like checking which threads are active inside of a certain divergent part of the code. All these kinds of intrinsics fall under voting across threads. So these are the two major types of intra-warp synchronization: sharing data or voting. So what are the different? Let's start by talking about the shuffle instructions. So what I will do in this lecture is I'm going to do two examples. I'm going to do one example where I'm going to show you how we can use shuffling on a pattern that we've seen before, and then I'm going to also do another example where I'll show you how to use voting. So let's start with the warp shuffle instructions. The built-in warp shuffle instructions enable threads to share data with other threads in the same warp. Now, previously, when we wanted to share data across threads in the same block, what we had to do is we had to declare something in shared memory. And then one thread would write to shared memory, and then we sync threads, and then the other threads will read from shared memory, and that takes a long time. So if we want to share data just between threads in the same warp, we can avoid that. So what we will be using the warp shuffle instructions, and that's going to be faster than using shared memory and sync threads. Now there are different variants of the warp shuffle instruction. There's shuffle sync, and what shuffle sync does is that it copies from it copies data from a specific lane, I'm going to use lane here to refer to one of the threads in the warp. So if a warp has 32 threads that execute in SIMD, we can refer to each of these threads in the warp as a lane in the warp. You can think of it as a lane in our SIMD or vector unit. Okay, so we can copy directly from a lane, from one lane to another lane. In other words, from one thread in the warp to another thread in the warp. There's shuffle up, and notice how there's underscore sync here. And the reason there's underscore sync is because when we use shuffle instructions, we're kind of synchronizing across threads in the same warp. And this distinction is actually important in the late generations of the architecture, of the GPU architecture, where they started enabling different threads to take different paths simultaneously. So you have different threads might have different program counters. And that's something that we didn't really cover, but this is part of the reason why we have underscore sync. So another one is shuffle up. And with shuffle up sync, you shuffle from a lane with a lower ID relative to the thread you're shuffling to. There's also shuffle down sync, and that's where you copy from a lane with a higher ID relative to the caller. And then finally, there's another example where you have shuffle XOR sync, where you copy from a lane using some bitwise XOR of your own lane. Now, having told you about shuffle, this idea of a thread wanting to get a value that was produced by another thread. Where have we seen this before? Which pattern did we look at where we had different threads producing values that later on another thread would read?
Histogram, maybe.
Now with histogram, all the threads were atomically incrementing the same value. That's not what I'm looking for. I'm looking for one of the patterns where one thread, you have different threads that produce a value, and later some of them read it. What did you say?
Is it scan?
A scan, right? Scan, exactly. So scan and reduction. So reduction is a simpler version of scan. So you're absolutely right. Reduction or scan. I'm going to focus on reduction because it's simpler. In reduction, the way reduction worked is that we had these threads all read some values and then produce a set of values. Okay, and then on the next step, some of the threads would read the values that different threads on the previous iteration produced. So here, thread 5 over here produced this value. On the next iteration, and then we had to do a sync threads, and on the next iteration, thread 0 was reading the value that thread 5 produced. Okay? And because we wanted all these threads to produce a value, and then we want to wait for them to finish before the threads can read these values, we had to do a sync threads in between each of the iterations of the scan. Now, when we looked at what that looked like at the warp level, if we have a thread block has 4 warps, on the first iteration, half the warps drop out, and we're left with 2 warps. On the next iteration, half the warps keep dropping out again until we're down to 1 warp. Okay, so between each of these steps we synchronize because we have threads in 1 warp need to read data that was produced by threads in a different warp on the previous iteration. But when we're down to 1 warp, for the remaining steps, the threads are going to be reading data that was produced by threads in the same warp on the previous iteration. So here in this warp, I have threads 0, 1, 2, and 3, right? On the next iteration, thread 0 is going to read the value that was produced by thread 2. Thread 1 is going to read the value that was produced by thread 3, okay? So when 1 warp remains, okay, the threads are reading values from the same warp. So what we can do is we can actually use shuffle instructions to do this instead of using shared memory and sync threads. Okay, in the previous implementation of production, what we did is on every iteration, we would store to shared memory and we would do a global async threads. Okay, but what we can do when we get down to the same warp is rather than using shared memory and sync threads, what we can do is we can simply shuffle the data from one thread to another thread. So here, each of these threads will add 2 elements and produce 4 values. And then in the next iteration, this thread 0, can shuffle the value from the register of thread 2 to the register of thread 0 without having to do any sync threads and without having to go through shared memory. Okay, is this clear? Any questions about this? I'll show you how we implement it, but conceptually, is it clear to everyone?
Doctor, why is it different? Because things in sync threads, no, the other threads are no, they're not doing anything أصلا. Why is it faster? لأنه shared memory is slower than
there's 2
shared
aspects. There's 2 things. So obviously, when we read from a register, is faster than reading from shared memory. But the key thing is that when I sync threads, what that means is I need to wait for all the warps to reach that sync threads before I can proceed. Okay, all the warps need to execute that sync threads before you can proceed. Whereas when we shuffle, we're only synchronizing across threads within the same warp. So we don't really care about what other warps are doing. We don't have to make sure all the other warps reach the sync threads. Okay, we're just thinking within the warp. That's why it's faster, because you know it's trivial to sync across threads within the warp because they're all executing in SIMD. They're all executing at the same time. So they all just reach the barrier at the same time quickly. Or they all synchronize quickly because they're scheduled together. Whereas when I do a sync threads, these other warps are not scheduled and they need to get scheduled to execute the sync threads and all that stuff.
Okay, I got it. Thank you.
Yeah. So the fact that the threads in the same warp are executing in lockstep makes synchronizing between them faster because they're executing at the exact same time. Okay, so let's go see how to implement this. I'm going to switch to the code over here. And this is the code that we wrote previously for the reduced kernel. Each thread took a segment that's twice as large as the number of threads that it had, and each thread was performing a reduction. So we started by loading the 2 halves of the input segment, adding them and putting them in shared memory. And then we continued by going from stride is block dim over 2 until the stride is 1, so greater than 0. And on each step of the way, what we did is the threads that were less than the stride would add the value that was stride away to the right. And at the end, thread 0 was responsible for storing the total sum of the total sum of the thread block and into the partial sums. And we dealt with the partial sums later on in a different way, either using by calling a reduced kernel again or by simply adding them on. So what we want to do is we want to change this reduction tree code so that instead of going all the way to stride 1 using shared memory and sync threads, we want to go until the stride is greater than the warp size with shared memory and sync threads. And once the stride is equal to the warp size, what we want to do is we want to read those values to a register and then continue in the registers and using shuffle instructions. This is what we would like to do. So here's how we're going to change the code. So here, we're going to do the reduction tree in shared memory, but we're going to stop once the stride reaches warp size. So we're going to go until, actually, let me first define a macro here that tells me what the warp size is. I'm going to do count define warp size. Okay. Okay, so what I will do is rather than stopping at 0, I'm going to stop at warp size. Okay. And now at the end of this iteration, what we have is we're going to stop when the warp size is 64, and this input underscore s is going to contain 64 different values that I need to continue the reduction on. So what will happen is in each thread is going to load 2 elements from shared memory, add them, and then that becomes the thread's partial sum. Okay, so now we're going to continue by doing the reduction tree using shuffle instructions. Okay, I'm going to initialize a value sum, and that value sum is going to be, so here when I'm down to a single warp, each one of these threads is going to load the value from the previous thread in the same warp, and the value from the previous thread in the previous warp from shared memory. So each thread will load two values from shared memory, and that will become the partial sum that this thread will produce. So here I'm going to start. I'm going to write. I will only want the threads in the first warp to compute. I'm going to write if thread index.x is equal to 0. And then these threads, sorry, not equal to 0. I apologize. I did that out of habit. If thread index.x is less than the warp size. Okay, so here I've excluded all the threads that are greater than warp size, meaning I kept only the threads that are within the same warp, the first 32 threads. Okay, now if the thread x is less than warp size, what I want the thread to do is I want it to load the value from the previous thread as well as the previous thread that's 32 away, and I want it to put that inside of some variable. So what I will write is sum is equal to input underscore s of thread index.x plus input underscore s of thread index.x plus warp size. Okay. So this here is basically the iteration for when stride is 32. So here we went from stride block dim over 2 to until the stride was greater than 32. And then now here I did the iteration where stride is 32. And while doing this iteration, I loaded my two values from shared memory and then put them in a register. Okay. And then for the remaining strides until we get to the last stride, which is stride 1, what we will do is we will read from the register and write to the register. So here we read from shared memory and wrote to shared memory. Here we read from shared memory and wrote to the register. And then for the remaining iterations, we're going to read from registers and write to registers using shuffle instructions, and we don't have to sync. All right. So we're going to do the remaining iterations now. We're going to do for unsigned int stride is equal to what? It's going to be equal to warp size over 2, right? Because we did block them over 2 until 2 times warp size here, and then we did warp size here, and now we're going to continue from warp size over 2. Okay, and then stride is greater than 0. Okay, and then stride is divided by 2. And then for each one of these iterations, what we did before is we did input of thread index.x plus equals input underscore s thread index.x plus stride. So we added the value that was stride away. We're going to do the same thing here. We're going to add the value that's stride away, but rather than getting that value from shared memory, we're going to shuffle it from the other thread. And this is how we do that. We're going to write sum plus equals. And remember, we have multiple shuffle instructions. We have shuffle. We have just shuffle where we get from a specific index lane, or we have shuffle down, or we have shuffle up. In this case, we want to shuffle down because we're shuffling from a thread that has a higher index. So I'm going to write sum plus equals, and then we will write shuffle down sync. Okay. And then we're going to provide mask. I'll tell you what that is later. And then we're going to provide the value that we want to shuffle. And in this case, it's sum. Okay. So each thread wants to shuffle its sum. We're going to provide the stride that we want to shuffle by, which is going to be stride. Okay. So here, what happens is when I write shuffle down sync, sum stride, each thread will shuffle the sum value of the thread that is stride away from it. Okay, each thread will shuffle the sum value of the thread that is stride away from it, and this value will be returned by the shuffle down sync instruction. And then now the thread will take the sum value of the thread that's right away from it, and it'll use it. In this case, it's going to accumulate it to its own sum. Okay. Now there's one thing left, which is this over here. This first field here specifies a mask. And this mask is going to specify what threads are going to be active during the shuffle down sync, because it's possible for me to only have some of the threads do the shuffle down sync and the others not do it. In my case, I'm just going to have all the threads do it. Okay, I'm not going to worry about keeping track. So I'm going to have all the threads shuffle down. So I'm going to just provide a mask that's all ones, and hence that's going to be F, 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 F. Okay.
Professor, you're cracking up a little bit. I'm not sure if it's from my side or yours.
It's fine for me.
Everyone else hears me fine? Okay. Okay, so we said that here when we say F, we're saying that all threads in the warp are going to be active. Now, for some threads, that if we go stride away from the thread, that value is going to be out of bounds. So in this case, the threads there are just not going to do anything. Okay. So here we're going to say that all threads are active, but then the threads where the threads that are trying to shuffle from a thread that's out of bounds are just not going to not going to do it. Okay. So by the end, what's going to happen is I'm going to keep doing this until I reach the last thread. And now the last thread will have the result inside of its sum variable. So now I go down here. Thread index x will equals 0. So thread 0 will have this value in sum. So here, rather than storing this value from shared memory or reading it from shared memory and storing it, we're going to just store the value that's written in sum. Okay, is this clear to everyone? Any questions?
Doctor, here, where are when thread index.x less than warp size, so when we're in one warp, where are the threads dropping out? Shouldn't the mask change?
So what's going to happen is, well, first of all, some of the threads are just going to be accessing data from out of bounds. So those are not going to be getting any useful data. But also, even if the threads even if the threads shuffle and garbage data, at the end we're only gonna use the sum for thread 0. So even if the other threads in the warp execute the shuffle instruction, we're not using their result. Okay, so we don't really need a boundary check over here.
Professor?
Yes?
Before we aligned the threads in such a way to reduce divergence, control divergence, but now that we have this shuffle, shouldn't we revert back where we can use shuffle on every warp at the beginning and keep the tree as it was before?
So I see what you're saying. So what you're saying is we can have each warp do its own local reduction using the shuffle instruction, and then each warp produces a partial sum, and then we have one warp reduce that partial sum using a shuffle instruction. Is that what you're saying?
Yes, because now there's no more divergence since every thread is doing the shuffle with garbage data, but it's still doing it.
Yeah. So you could do that. That's perfectly fine. If you think about that, each warp is going to have its own local divergence happening, right? So here we drop out half the warps every iteration. When we do it this way, we're dropping out half the warps every iteration. Whereas if you want to do a local shuffle in each warp and then do a shuffle of the partial sums of each warp, all the warps are going to be active on each iteration. Okay, so we haven't really gotten rid of divergence here in the sense that some threads are going to be doing some work, but that work is not going to be used.
Right, I see.
Yeah.
Okay.
No, I'd rather have half the threads work and half the threads drop out than to have all of them work using shuffle instructions and not sync at all. But I mean, if you want to implement that other version and try it and see if how well it performs compared to this one, that would be interesting. That'd be an interesting exercise.
Professor, can you just repeat what the shuffle down sync does?
So what shuffle down sync does is that it takes a value from a thread that is stride away and shuffles it down to some thread. Okay. So here, what shuffle down sync will return is the sum register of the thread that is stride away from me within the warp.
Oh, okay. Yeah. What's the 0xFFF?
So again, this is the flag. It's a mask. It specifies what threads in the warp are going to be active during this shuffle operation. Okay, in this case, I'm just making them all active because I'm not going to use the results of the result of the threads that I don't need. Okay.
Okay, good.
Yeah. You'll see another use of this mask later on when we look at voting. Okay, so let's compile this and run it and see how it performs. And I just realized that I actually forgot to compile it and run it before I implemented this. Let me do that. I'm gonna undo. Okay. I'm gonna save. I'm gonna compile. This is the old code, just to show you the performance of the old code. Okay, so it took around 2.1 milliseconds in the old code. Now let me go back and open this. Oops. I'm gonna redo. Okay, and I'm going to close it this time. I'm going to compile, and I'm going to run it. And as you can see, we have significant performance improvement compared to the version of that shuffle instruction. Oops! Somebody just notified me that my screen is frozen. Can you see? Can you see now? Okay. So this was the performance that we got when we ran the version without shuffles, and this is the performance that we got when we ran the version with shuffle. Okay, so as you can see, the execution time with shuffle is much faster than the execution time without shuffle. Okay. Is it clear? Any questions? This is the code again. Okay. So that is kind of one example and one popular example of where we can use shuffle instructions. Whenever we want to share values across different threads in the warp, especially if we're trying to have these threads collaborate and to perform some kind of reduction. It could be a sum, it could be a min, it could be a max, etc. And here, this is the code that we just wrote. The next category of intra-warp synchronization instructions is the warp vote instructions. And the built-in warp vote functions enable threads to vote on which threads in the warp satisfy some condition. And there's different variants of the warp vote. One of them is all sync, which takes a mask of the threads that participate in the shuffle instruction, a predicate, and checks if the predicate is non-zero for all of the participating threads. Okay, so checks if all threads in the warp satisfy some condition, or their value satisfies some condition. There's AnySync, and AnySync it also takes a mask of participating threads and a predicate, and checks if one of at least one of the threads in the thread satisfies the condition, or it checks if the predicate is non-zero for some thread in the warp. Okay, so here we check if all the threads satisfy some condition. Here we check if any of the threads satisfy some condition. Another one is ballot sync, and what ballot sync does is that it takes a mask, again, of the threads that are participating, and a predicate, and it returns a mask that has a bit set for each thread that evaluates the predicate to non-zero. Okay, so it gives me a 32-bit integer, and a 32-bit value is going to have 1 bit that corresponds to each thread in the warp, and that bit will be set to 1 if the predicate is non-zero, and it will be set to 0 if the predicate is 0. Okay, so this doesn't just tell me which threads satisfy the predicate. It also tells me, this doesn't just tell me if the threads satisfy the predicate. It also tells me which threads satisfy the predicate. And then the other interesting one is active mask. An active mask basically tells me which threads are active in a particular at a particular point in the code. And this is useful when we are doing these warp shuffle instructions in a place where we have control divergence, because this allows us to know which threads are active in this branch of the code and which threads are not active. So somebody asked me that before. They told me, how can we know which threads are active and which threads are not? And this is how you can do it using the active mask. Somebody's asking, what can the predicate be? The predicate can be anything. I mean, some condition. Okay, that you want it could be true. That could be true or false. You basically just care if it's 0 or non-zero. Okay. Now, to show you an example of where something like this might be useful, let me show you another simple code that enqueues stuff to a queue. So let's go. I have another.
Professor, can voting in this case be useful for debugging purposes, for example?
I mean, usually when you have something like this, it's not provided for debugging. It's provided because it's useful in the actual computation. If you have some situation where you want to use it for debugging, I mean, you can use it, of course, but that's not the primary objective of providing it. The primary objective of providing it is to be able to synchronize, have threads collaborate to do something together. Okay, and I'm about to show you an example of where it could be useful. So here, what you can do, I have an enqueue kernel, and what this enqueue kernel does is that it has some input, it reads a value from this input, it checks some condition on this value, and if the value satisfies some condition, it's going to add the value to a queue by atomically incrementing the queue size, getting an index into the queue, and then adding the value at that point in the queue. Okay, so we've seen queues before. Okay, we've seen queues before with BFS. I didn't want to have a full-fledged example here with queue just to keep things simple. So here we just have a queue, and all the kernel does is check a condition and add something to the queue. Okay, this code could be inside of a kernel where there's much more context, where there's much more complex work happening before we add things to the queue. But I just using this as a simple example so that we can avoid having all the noise from other examples, and then just focusing on the action of adding to a queue. Now, why is this interesting for shuffle instructions? Well, as you can see in this example, all the threads in the thread block are incrementing the same variable to add to the queue. Okay, and so they're atomically incrementing the same global variable to find where they need to add to the queue, and then they add to the queue. Now, previously we optimized this using privatization, where we declared a private queue in shared memory, and then had all the threads add to that shared queue, and then wrote that shared queue out to global memory. Another thing we could have done is we could have had, rather than every thread, we could have looked at each warp, and rather than every thread in the warp doing an atomic add, we can have the threads in the warp collaborate with each other to figure out how many threads in the warp want to add to the queue, and then have only one thread in the warp do an atomic add, and then have all the threads in the warp write out their result to the queue at the location that the leader thread or that one thread that did the atomic add reserved. Okay. let's see how we can do this. Is it clear to everyone what this optimization, what we want to do is? Rather than having all threads in the warp, each of them increment the global counter, I'm gonna have them collaborate with each other to find out what is the total number of values that this warp wants to add to the queue, and then we do one atomic add for the entire warp, and then we have all the threads in the warp collaborate to store their result at the right point in the queue. Okay, is it clear? Okay, well, let's see how we can do this. First of all, this is the original in-queue code that I just showed you, and we observed that the atomic add here, we have all the threads contending on the same variable to reserve space in the queue, and what we want is to optimize this by doing one atomic add per warp. So here's what we can do. We can optimize this with warp votes. So we can have only one thread in the warp increment the global counter on behalf of the others, and then have all of them store to the queue. And here are the steps that we're going to follow to do this. The first thing we're going to do is we're going to assign a leader thread. So we're going to assign one thread in the warp that's going to be a leader thread that's going to lead all the other threads in the warp. Then what we want to do is we want to find how many threads in the warp want to add to the queue. Once we know how many threads in the warp want to add to the queue, we're going to have the leader thread perform an atomic operation to reserve that much space in the queue. And then once the leader thread reserves that space in the queue, the leader thread is going to broadcast its result to all the other threads. And then once we broadcast the results to all the other threads, each of the thread is going to figure out its offset for its own result from the location that the leader thread reserved, and it's going to store that result. Okay, is this sequence of steps clear? I'm going to show you how we're going to implement each of these using the warp vote functions, but is this clear? Okay, so let's start with the first step, which is assigning a leader thread. So what we'd like to do is we'd like to assign a leader thread. And the way that we can, to assign a leader thread, can we just say that thread 0 is the leader? Right, can we say that thread 0 is always the leader?
Yes,
I guess you
because
have
it's
to make
always
sure
there.
that it doesn't drop out.
Right, exactly. So here, I want to replace this atomic add code with code that has has one thread do on behalf of all. So here, first thing I want to do is I want to assign a leader thread. So somebody said that we had to make sure that thread 0 is, we can't just say thread 0, because thread 0 may not pass the condition. So thread 0 may not reach this point. Okay, thread 0 may not reach this point in the code. So what we want to do is we want to assign a leader thread. And the way we can assign the leader thread is we're going to identify which threads are active. And then we're going to pick the first active thread in the warp. Okay, we're going to identify which threads are active, and we can pick the first active thread in the warp. So how do I identify which threads are active? We saw a warp vote function that gives us that. What was it? Does anybody remember it?
Any sync or ballot sync?
No, it was it wasn't ballot sync. It was active mask. Okay, so we're going to find which threads are active using the active mask. So the active mask is going to contain a bit set for each thread that is active. Okay, so the way I'm going to do that is as follows. I'm going to write unsigned int active mask. Okay, is equal to, or let me, to avoid confusion, I'm going to call this active threads is equal to __ active mask. Okay, just don't want to name it the same name as the function itself. Okay, so by calling active mask, this returns a 32-bit integer that has a bit set for each of the active threads. Somebody has a question?
As you said, it has one bit assigned per active for each active thread. So shouldn't it be a byte instead of an int?
No, because we have 32 threads in the warp, so we need a 32-bit value.
Oh, okay.
To be an unsigned int. Okay. Okay, now that I know the active threads in the warp, the next thing, so for example, if threads 1, 2, 4, and 5 are active, then the active mask is going to look like this. I'm going to have the zeros for the inactive threads, and I'm going to have ones for the active threads. So here, threads 1, 2, 4, and 5 will have their active, will have their bit set in the active mask. Okay. Here I'm using an 8-bit example, but in practice you have 32 threads in the warp, so you're going to have a 32-bit mask that gets returned. Okay, now what I want to do is remember I'm trying to assign a leader here. So what I want to do is I want to pick one of these threads to be the leader. Okay, how can I pick one thread to be the leader? Well, I can simply pick the first thread in the warp to be the leader, and to do that, there is actually an intrinsic function that tells us that gives us the first bit that is set in a particular value. Okay, so I want to designate the first active thread as the leader, and to do that, what I want to do is I want to find the first set bit in the active mask. So in this case, I want thread 1 to be the leader. So I want to find because the first set bit in the active mask is the one that corresponds to thread 1. Now there is a built-in intrinsic function that does that, and it's called FFS, find first set. And FFS, find first set, this is not a warp level intrinsic, okay? This is just an intrinsic function, but it's not a warp level thing. Each thread executes its own FFS. The threads are not collaborating here. So FFS takes some 32-bit value and tells you what is the first bit that is set in that value. So it's going to return the index of the first set bit in the mask. Now, one thing to note is that the index that it returns starts from 1. Okay, so if thread 0, or if the value at position 0 is the first set bit, it's going to return 1. If the value at position 1 is the first set bit, it's going to return 2. If the value at position 2 is the first set bit, it's going to return 3. The reason is that the return, it could be possible that none of the bits are set. Okay, and in this case, we want it to return 0. Okay, so if none of the bits are set, it's going to return 0. And then if bit 0 is set, it will return 1. If bit 1 is set, it will return 2, etc. Okay, so in this case, what will be my result when I call FFS on this active mask?
2.
6.
2, right, it's going to be 2. Because the first set bit is 1, so it will give me 2. So the indexing starts from 1. So for me to identify what is my leader thread, I'm going to call FFS. So I'm going to write unsigned in leader. So this is going to be the index of the leader thread within the warp. Okay. I'm going to write leader is going to be underscore underscore FFS. So find first set of the active threads mask. Okay. And then what do I need to do? Remember, this is indexed by 1. So I'm going to have to subtract 1 from it. Okay. So that I get a value that's indexed by 0. So here, if thread 0 was the first, if the thread 0 was the first active, sorry, if bit 0 was the first active bit, then the leader is going to be thread 0. So FFS will return 1, and I subtract 1, I get 0. If bit 1 was the first active bit, then FFS of active threads will return 2, and then 2 minus 1 will be 1, so the leader will be 1. Okay, so now what I've done is I've assigned a leader for the threads in my warp that are active inside of this condition. Now that I've assigned a leader, the next step is for me to find out what is the reason I'm assigning a leader is because I want the leader to allocate space in my queue on behalf of all my other threads. Okay. So what I will do next is I want to find out how many threads need to add to the queue. So I'm going to what I want to do. I want to allocate space for all the threads to store. So I want to find out how many threads need to add to the queue. So the way I will do that is by how do I find out how many threads need to add to the queue? I have the number of threads that are active, or I know which threads are active. So how can I know how many threads are active?
We need to count the number of ones.
Right, we need to count the number of bits that are set in my active threads mask. Okay, so we need to count the number of set bits in the active mask. And there's actually another intrinsic that takes a 32-bit value and counts the number of bits that are set in that value. Does anybody know it? It's actually it's a popular name. It's not just in on GPUs. So it's called population count. You guys familiar with population count? So population count, POP-C, is an intrinsic that takes a 32-bit value and returns the number of bits that are set in that 32-bit value. Okay. In the previous example here, if I call POP-C on this active mask, it's going to give me 4 because there are 4 bits that are set. Okay. In general, POP-C will give me however many bits are set in that value, and that's going to be the number of threads that are active, which is basically the number of, excuse me, it's basically the number of elements that I would like to reserve in my queue. Okay. So next we're going to find how many threads are active, and the way we do that is as follows. We're going to write unsigned int num active is equal to population count of active threads Okay. Now that I know how many threads are active, I want the leader thread. Here we're going to have the leader thread perform the atomic operation. Okay, we're going to have the leader thread perform the atomic operation. So how much does the leader thread need to allocate to the queue? Well, it needs to allocate to non-active element. Okay, so we're going to have leader allocate in queue. Okay, so we're going to have unsigned int j. J is going to be the position where the leader is going to allocate to the queue, and we're going to check if the thread is the leader. So I'm going to write if thread index.x. Remember, I want the index of the thread within the warp, not within the block. So how do I get the thread index of the thread within the warp?
Modulo warp size.
Right, exactly. If I do thread index.x modulo warp size, I need to define warp size up here. Okay, I'm going to do thread index modulo warp size, and if that is equal to the leader, okay, so here only the leader thread is going to pass this check. And then if thread index modulo warp size is, if the thread is the leader, what's the thread going to do? It's going to do atomic add. And it's going to add to the queue size. Here, the queue size tells me how many elements are in the queue so far. So I'm going to increment the queue size by the number of active threads, which is the number of elements I want to add to my queue. And the return value is going to be the old value of queue size, which is the position that I want to enqueue all the warps values. So I'm gonna set this to j. Okay. Now that I do this, what I want to do is I want to broadcast the result to the other threads. Okay, so whatever the leader thread is, I want to take that result and broadcast it to all the other threads. Okay, what can I do to do that? So if warp 0 has a value, which is j, or no warp 0, the leader thread has a value, which is j, and it wants to send this value to all the other threads. So what can it do that? What can it do to do that?
Shuffle up.
Well, just shuffle. You can just shuffle. So remember, what we're going to do is we're going to write A is equal to shuffle. So here, for at this point, only the leader thread has the right J. I want all the threads to have the right J. So I'm going to write J is shuffle sync. Okay. And I need to provide it a mask with the threads that are going to be involved in the shuffle instruction. I need to provide it the value that I want to shuffle, which in this case is J, and I need to provide it where the way shuffle sync works is I provide the index of the lane I want to shuffle from, which in this case is the leader. Okay. So what this is saying is that shuffle the value of j, so shuffle the leaders j to all the other threads, and now this shuffle sync will return j, the leaders j for all the threads, and all the threads will initialize their j to that. Now I need to have here the mask that tells me which threads in the warp are going to execute the shuffle sync instruction. So which threads in the warp execute the shuffle sync instruction? Can I do this?
No, it's the active thread that we got from active mask.
Right, exactly, because not all the threads are active at this point. What I'm going to do is I'm going to provide the active threads which are in the active, which I got from the active. Okay.
Can the thread
So
include
now-
it?
Sorry, question.
Yeah, sorry. Can the thread shuffle to itself? Will it work or do nothing?
That's fine. I mean, if here it shuffles to itself, is just going to keep the same value and store it. So here the leader thread is just going to shuffle its value to itself.
Okay.
So it's not going to change. Okay. So now every thread knows the starting point of where it needs to store in the queue. So if there are 10 threads that are active in this warp, the leader is going to allocate 10 elements in the queue. Okay, and then this J here is going to point to the beginning of those 10 elements. So what's left for me to do is each thread needs to figure out which of those 10 elements it needs to store to. Okay, figure out which of those 10 elements it needs to store to. So what we still need to do is we need to find the position of each active thread in the queue. Let's take a look at how to do that. By the way, here the broadcast that we use shuffle. Okay, next step is we want to find the offset of each active thread and store the result. Now let's take a look. In the previous example where we had this, okay, we would have allocated the leader thread would have been thread 1. Thread 1 would have allocated 4 elements in the queue, and then starting from that 4 elements, thread 1 is going to store its result at an offset of 0. Thread 2 stores its value at an offset of 1. Thread 3 doesn't have anything, so thread 4 is going to store the value at an offset of 2. Thread 5 at an offset of 3. Okay. So what each thread needs to find is where it needs to store its value in the queue. How can I do that?
We need some sort of scan.
Right, it's similar to scan, but we can do it more efficiently than scan. But you're correct to observe that there's something similar to scan, and that what do we need to find?
Can we do an bitwise and select up to the thread that we're at, and then count them using the function we used before?
You're absolutely right. Absolutely right. So basically, what we need to do is we need to find the number of previous threads that are active. Okay, what we're trying to find here is the number of previous threads that are active. So here, the reason thread 1 is 0 is because there are 0 active threads before it. The reason thread 2 is 1 is because there's only 1 active thread before it. The reason thread 4 is 1 is because there are, so the reason thread 4 gets 2 is because there are 2 active threads before it. The reason thread 5 gets 3 is because there are 3 active threads before it. So what we want to do is we want to count the number of ones in the previous threads. To do that, what we can do is we can do a bitwise AND to keep only the ones of the previous threads and remove the ones of the threads that come later. Okay, and then after we do the bitwise AND, we do a population count. Okay, so here, what we'll do is we'll, for an example, if we want to find for thread 4 what its offset is, we're going to do a bitwise AND with a mask that contains ones for all the threads whose index is less than 4 and zeros for all the threads whose index is greater than or equal to 4. And when we do a bitwise AND over here, we get the number of previous active threads. So this was the number of active threads. This mask represented the active threads. This mask represented the previous threads. And then when we do a bitwise AND of them, we get a mask that represents the previous active threads. And then once we do a population count on this, we will get the offset that we are looking for. Okay? So we have an active mask, we know how to do a bitwise AND, and we know how to find the previous active. We know how to do a population count. How can I get a mask that tells me what are the previous active threads?
It's the current index minus 1 in decimal, so you can get that in hex.
So it's not the current index, but I know what you mean. You're saying it's a bit set for the current index, and then I subtract 1 to get a bunch of 1. So here, if I want to get the previous threads mask for when the thread index is 4, I'm gonna start off with something where I have a value where I have 1 set in position 4 and 0 otherwise, and then I subtract 1, and that gives me 1s for all the other threads before the thread 4. Okay. So basically what we're going to do is if the thread index is 4, we're going to shift a 1 by the thread index. That'll give me 1 in position 4. And then we're going to subtract 1. That's going to give me a bunch of 1s in the previous position. Okay? So we're going to shift 1 by the thread index, and then we're going to subtract 1. All right? Let's see how we can do that. I'm going to come back here. So what I'd like to do now is I would like to do, first I want to find the previous threads. We're going to do it by shifting 1 by the thread index and then subtracting 1. So I'm going to do, previous threads. So this is the mask for the previous threads. And what I want to do is I want to take a 1, and I want to shift it by the thread index. What is the thread index? How do I find the index of the thread within the warp? I've done it before, right? Take thread index.x, and I do modulo the warp size. Okay, so I shift a 1 by that amount. Okay. Let me put some parentheses here to be certain, clear what I'm doing. So I get the index of the thread within the warp. I take a 1 and shift it by that amount. So this value is going to give me a 1 set in position 4 and 0s elsewhere. And I'm going to subtract 1 from that. Okay. So I'm going to subtract 1 from that, and this will give me the previous thread. Okay. Now that I have the previous threads, I want to find the previous active threads. So I'm going to do a bitwise AND between the previous threads and the active mask. Okay. Somebody had a question?
Yes, don't we have arithmetic shift? That way the 1 is replicated without having to do the -1.
That's if you shift right.
Oh, okay. We can't.
Are
shift
you
left.
talking about int versus unsigned int?
No, I was talking about arithmetic shift where the 1 is replicated, but maybe it's only for shift right. I'm not sure.
Oh, I see what you mean. So you want to shift. You want to take a 1 and you want to shift it thread under thread x on your warp size -1 time. Where you shift and you just get a bunch of 1. That's what you're saying.
Exactly.
Yeah, I'm actually not sure if that's supported. Might be.
Professor, there is one thing I don't understand. So the thread index indices are set at the block level. We don't actually know within the warp which threads will execute, right?
You mean, well, we know the index of the thread within the warp, which is this. We can get it by doing modulo warp size.
But it might, so thread number 2 might execute along with thread number 234. That's
No, because threads in the same warp execute in SIMD, right?
Yes.
So threads 0 to 31 are in one warp, threads 32 to 63 are in the next warp, etc.
Oh, okay. Because I thought you could mix them up within the same block.
No, the threads are assigned to warps based on their index.
Oh, okay.
Yeah. So all the threads in the same warp have to be the consecutive threads. Okay, so now we're going to find the previous active threads by doing a bitwise AND between the active threads and the previous threads. Okay. And then after that, what we want to do is, once we find the previous active threads, we want to count the number of ones inside of it. How do we do that?
Popsy.
Right, exactly. We're going to use a population count in order for us to count the number of set bits in the previous active threads. So here, the offset is going to be equal to the population count of the previous active threads. Okay, and then now what's left for me is to store the result in the queue. So I will write queue of something is equal to my value. Okay, and here what is the index into the queue? It's going to be the starting position that the leader thread obtained, which is J, plus the offset that each thread found for itself. So J plus offset. Okay? This is clear to everyone? Questions? All right, so let's compile this and run it. And I just realized that I did the same mistake again. I forgot to run the version without this optimization. So let me undo all the way. So I'm going to compile the old version of AQ, and I'm going to run it. So here you'll notice my kernel time is 0.39. And now let me redo. Okay, I'm going to compile now the new version, and I'm going to run it. And you'll notice we actually hurt performance a little bit. Okay, the reason is that I tried to kind of have a focused example, and because I had a focused example, the overhead of doing the warp synchronization was actually not worth the atomic operations that I avoided. Okay, so in this particular example, it hurt performance, but in other examples where there's perhaps more going on and there's more context to the problem, this approach of collaborating across threads to do something together is actually an effective one. Okay, so I apologize if you're disappointed that there's a little bit of performance degradation, but I at least hope that this exercise gave you kind of a hint at how we can use all these different how we can use all these different intrinsics like the active mask, the find first set, the population count, and the shuffle instructions in order for us to do some kind of collaboration between threads in the same warp so that they can collectively accomplish a common objective. Okay? Any questions? Okay, well, this is the code that we just wrote, and this is also the final slide I have for today. Does anybody have any final questions before we conclude?
I have questions about the project.
Okay, sure. Feel free to ask me after.
Okay.
Okay, if there are no final questions, then that's all for today, and I'll see you next time. Bye, everyone.